Hello everyone, my name is Don Kasper. I'm a senior engineer and senior building energy analyst for Stephen Winter Associates, headquartered out of Connecticut, but I actually work out of the New York City office. And I'm here to present the webinar, Assessing Energy Efficiency in Commercial Buildings, to you. I'm here at the onset headquarters in Cape Cod, Massachusetts, actually today. And hopefully I'll be able to open up the world of energy efficiency in commercial buildings to you guys. From the perspective of an energy engineer and an energy consultant. To give you a little bit of background, I work in the commercial energy group at Stephen Winter Associates. I specifically deal with commercial buildings in all sizes, from 5,000 square feet to we just completed a 2.5 million square foot project. A lot of my focus is on energy auditing and other energy services related to energy auditing. I work a lot involving LEED EBOM certification. For those of you who don't know, that's LEED Existing Buildings Operation and Maintenance. And I'd like to ask that if there's any general questions, I'd like for people to hold off on the questions until the end of the webinar. If there's questions pertaining to a specific slide or a specific topic, you can type it in, and I'll see it pop up on the screen here. But I may ignore it if it's going to disrupt my flow, and try to answer it at the end. Any questions that I don't get to, we can send you out a written response after the webinar. We're hoping that it'll take about an hour and 45 minutes of actual presentation material, which will leave us about 15 minutes at the end to either extend the presentation a little bit or answer any questions that you guys may have. So to give you a little bit of background about this specific webinar, really the goal of this webinar is to give you an introduction to energy efficiency in commercial buildings. Like I said, from the energy auditing, energy consulting perspective. We're going to discuss the different rating system standards kind of surrounding the world of energy efficiency right now in the United States and abroad, and also just discuss common energy conservation measures. You'll hear me refer to them as ECMs throughout the presentation. And things such as utility bill analysis and other further energy analysis based off those utility bills, based off data collection, and based off data logging with different types of sensors and data logging equipment. Just as a quick disclaimer, the views and opinions are mine. I've learned that a lot of engineers, including myself, can be pretty hard-headed. A lot of these slides, you'll see energy conservation measures. They're not supposed to be absolute recommendations, but given certain circumstances and certain conditions, they have worked. We've implemented them on various projects. So just like to give you that disclaimer. Again, this is an overview. A little bit about the background of the presentation is that it originally started out as a 16-hour training opportunity for a utility program in the Northeast. It kind of got condensed down, presented as a USGBC course, as a 3-hour, 3-credit course. We've whittled it down to about 2 hours now in this webinar format. For those of you wondering, you will be receiving, probably within the next day from me, those who attended, continuing education certificate for 2 credits for USGBC and GBCI continuing education credits, as well as kind of a brief survey just of how I did and how the presentation went, and if it was applicable to you and how it can be improved. So that will be coming to you guys via email. I'd appreciate it if you guys could fill out the survey and send it back. Again, it'll probably come to you tomorrow to your email inbox. And lastly, please consult with a professional for your application. As funny as it may seem, I have had people take slides literally and not know what they're doing and go and apply these concepts to a building without fully understanding what was involved. So if you have a question, just ask, and always consult with a professional before your application. To give you a general overview, we're going to talk about current issues, kind of the energy efficiency world as it relates to kind of national resources, kind of the over driving themes of this presentation. How building energy efficiency and building energy use fits into those recurring themes, such as greenhouse gas emissions, pollutants in the atmosphere, water consumption, and then get into building specific energy conservation measures. We'll talk about ASHRAE energy standards and the different levels of effort associated with ASHRAE energy audits. We'll talk about benchmarking with two different EPA softwares. One is Portfolio Manager, the other is Target Finder. We'll give you a brief example of those and talk about the calculations behind them. We'll talk about a preliminary energy analysis using your utility bills, extending beyond that and addressing data logging and using kind of instrumentation to collect data in the field and taking your energy analysis a little bit further. We'll go over a few case studies, lead and ASHRAE standards, and common examples, case studies, and energy conservation measures. So again, if you guys hear me refer to ECMs, I'm referring to energy conservation measures. And those are your actual recommendations. Here's just a quick quote. This is actually taken out of Building Owners and Managers Association magazine. Really the overall theme here is that energy efficiency fits into the commercial building field, not just from a good conscience perspective, but also means energy savings, a healthier work environment for the workers, and actually increasing the asset value of portfolios of buildings in the commercial building world. One thing that once you step into the commercial building world, you'll see that there's advantage to be had over competitors. There's a lot of building management and building owner companies that have to do with commercial buildings, and those buildings are their assets. There's an advantage over competitors for leasing space. You'll see that a lot of people now, specifically in the New York City area, we're seeing it now is a lot of green leases factored in. A lot of tenants are being responsible and have a lot more responsibility on them for how much energy they use, and also are more aware of how much they're paying for energy. So you'll see that there's an advantage over competitors, that people want to work and live and manage green buildings. Reduce operating costs, not only on the energy side, but also on the operation and maintenance side. An increase in occupant productivity and health. Typically, sustainability is associated with a healthy environment and also with energy efficiency and environmental responsibility. And that's having the good conscience to know that reducing energy consumption at your building is also reducing greenhouse gas emissions and overall making a better world for us to live in. Out of the total energy consumption for the United States, commercial buildings took up about 18% of total energy consumption. By the time you add in residential buildings, it's 39% total, just for building usage. Once you include such factors as transportation of raw goods, industry, the construction trades, and how much energy is used for building and maintaining a building, we go into well over a majority of energy consumption is associated with the building industry in the United States. This chart is taken right out of the US GBC manual. The overall 71% of total electric consumption is caused or used by buildings, 65% of total waste output, 39% of CO2 emissions, and 12% of water usage. So going through programs like LEED certification of buildings, you can see that there's actually a big environmental impact that we can have on the national level through the use of buildings. Saying and recognizing how much impact we can have on buildings, we see that we can reduce of that percentage that's used of the total U.S. energy consumption dedicated towards commercial buildings. We can reduce solid waste 70%, water use 40%, CO2 roughly 33%, and energy use at least 24%. So how do we actually reduce energy consumption, and where do we start? If you're a building owner or manager, you're involved with buildings in any capacity, there's two really standout programs or certification programs that you'll hear kind of as buzzwords right now. They're highly recognizable, but the most recognized being Energy Star and LEED certification. The big difference is Energy Star is really a rating system that rates your building on a scale of 1 to 100. In order to achieve Energy Star certification, you'd need to achieve 75, which equates to the 75th percentile on a scale of 1 to 100 for building energy usage. This certification program is a lot more objective, meaning that as long as you achieve that 75%, using your utility bills and putting it in the program while maintaining health and safety conditions, ventilation, you're going to get an Energy Star certification. LEED existing buildings, again, it's LEED EBOM. The big difference here is that it also includes things like sustainability, sustainable sites, materials and resources. It cares more about things other than energy, including energy, such as where the different raw goods at the site were sourced from, cleaning products that you may use, other things having to do with ventilation, and really the health and the environment of the building, as well as energy consumption. So Energy Star certification, like I said, in order to achieve the certification, you need to have a score of 75 or higher. The certification is really based on the integrity of a professional engineer. Those that vouch for a building and stamp it are agreeing that they didn't sacrifice ventilation or health and safety codes in order to reach a score of 75%. Yeah, this is a typical statement of energy performance you'll see with the engineer stamp on it. That's what will be submitted in order to achieve the plaque or the signage that comes with certification. And I'd just like to point out, too, that Energy Star, because Portfolio Manager is widely recognized, which is the front-end software, it's online, it's free. It plays really well with LEED. Some of the prerequisites and credits actually require you to use Portfolio Manager or an equivalent, and we'll get into that in just a few minutes. What's great about LEED is that there's a lot of parts that not everyone agrees with, but it is a voluntary, consensus-based national rating system. There's a lot of committees and subcommittees that make up and help set up the technical standards. It references a lot of standards such as ASHRAE 90.1 and ASHRAE 62.1. For those of you who don't know, ASHRAE is American Society of Heating and Refrigeration and Air Conditioning Engineers. They're a body that produces a lot of standards that are adapted by building codes and rating systems such as LEED. This focus is going to be on sorry, if you guys have had issues with audio, we're still trying to make some fixes on our end. Really, this presentation is going to be focused on existing buildings. So from here on out, I'll be referring to LEED EBOM. But just to show you a comparison for the 2009 version of LEED, for both new construction and existing buildings, there's a total possible points of 110 for each program. Of those 110, we have 35 points dedicated to energy and atmosphere credit. That means that every building that's LEED certified had to achieve or had to make a significant impact on energy efficiency and energy use in order to get the LEED certification. And you can expect to see this number grow as different iterations of LEED certification come out. Like I said, LEED focuses on other things other than energy efficiency. It focuses largely on sustainability, sustainable sites, water efficiency, energy and atmosphere, materials and resources, and also indoor environmental quality. A lot of these different categories play together. Indoor environmental quality sets standards for how much ventilation is needed, how much outside air is brought in on a per-person basis and on a per square foot basis. In addition to improving indoor air quality, this also gives us opportunity to make energy efficiency improvements. Also on the water efficiency side, energy and atmosphere credits do combine with water efficiency in categories such as condenser water and water efficiency involving the HVAC systems. So today's focus is really going to be on the energy portion. For those of you who aren't familiar with the LEED EBOM scope of work, we really have two main prerequisites, which means they're mandatory. All right, we're going to try switching over to a phone. Can anyone hear better now? Okay, sounds good. All right, so we're on a handset right now. So for those of you who aren't familiar with the LEED EBOM rating system, there's two real prerequisites. required for the energy and atmosphere credits. Prerequisites meaning that in order to get LEED certification, these are things that you have to do, that there's no credit associated with them. These are mandatory requirements, the first being EAP1. That's the typical notation to refer to prerequisite 1 in the energy and atmosphere category. Every building, existing building, going through LEED certification must have an ASHRAE Level 1 energy audit conducted. We'll get to that in a few minutes as to what the different levels of ASHRAE energy audits are. But as a prerequisite, every building has to have an ASHRAE Level 1 walkthrough audit completed. The second prerequisite, EAP2, the building must have an ENERGY STAR rating using the Portfolio Manager software of at least 69, or show that the building performs at least 19% better than average for typical buildings of similar type. Getting into the credits, so these are actually credits that, out of that 110 points that we referenced before. There are credits associated with these that are necessary to achieve different levels of certification. So for achieving 69 on the Portfolio Manager software, you're eligible for LEED certification. Starting at 71 points, there's additional credits available for achieving different milestones above that. We'll see a chart in a few minutes. And then EAC 2.1, the credit 2.1 under the energy and atmosphere. There's a choice to be made that the building must undergo a commissioning process track that includes implementing a commissioning plan, following through with implementation, and then doing commissioning after energy conservation measures have been made, or conducting an ASHRAE Level 2 energy audit. So to delve a little bit further into ASHRAE energy audits, the main theory is that you're going to collect and analyze historical energy use. The best practice would be to obtain at least 24 months of utility bill data and analyze the most relevant and the most recent data using the second year of backup data to adjust any anomalies and to ensure that there were no outliers in the data. Also look at the building and operational characteristics. Look for outliers in the operations of the building, performing energy and economic analysis for changes, and provide a list of ranked modifications in the form of energy conservation measures. There's 3 basic levels of energy audits under ASHRAE. Level 1 is really a walkthrough survey. So again, this slide is just showing the theory of an energy audit. I'm going to go through the levels in a minute. But it's really to establish building conditions, it's benchmark and evaluate how the building's performing, assess the list of opportunities based on the performance of the building, assuming that your building's not perfect, which very few, if any, are, and then also implement recommended measures and turn to energy use. So level 1 energy audit is really a one-day facility walkthrough for most facilities. It's really focused on operation and maintenance, conditions of a building, and measures. It's looking at how a building's operated, factors such as the temperatures, occupancy, things that can be changed at low or no cost. Giving an estimated breakdown of energy consumption by end use, so how much of energy goes towards heating, cooling, lighting, domestic hot water, and then identifying those low-cost changes and estimated savings, and identifying maybe big-ticket items such as chiller replacements, boiler replacements, system redesigns that would be good to study further and maybe conduct a feasibility study. A level 2 energy audit, so again, this is for credit 2.1. This is one of the options. Hang on one second, there's a question. For the person who asked, this is for existing buildings. So this would be for any existing building that falls within the definition of a commercial building under the LEED E-Bond category. So the level 2 really builds on a level 1 audit. It's still looking at those operating parameters, but it's also looking at kind of low-cost measures, maybe that fall within a 5-year payback period. This is where you start to actually look at and collect data, looking at supply air temperatures, supply and return water temperatures, operating schedules, and doing a little bit in-depth analysis and giving some financial perspective on measures other than operation and maintenance that can be addressed in the building. And again, just to bring up credit 2.1, since we've defined ASHRAE level 2, is that there's two options. There's a commissioning process, like I previously stated, that's developing a retro commissioning plan, moving forward with implementation, and then tracking the energy use. There's different credits for each different phase. So there's more credits on that path, but there's also ASHRAE level 2 energy audit, which is doing a one-time ASHRAE level 2 energy audit, submitting a report, and showing that there are opportunities other than operation and maintenance that were researched and studied within the building and recommended to the building owners and management. Since I mentioned commissioning and retro commissioning, I'd just like to mention it here again. LEED really defines 3 different types of commissioning. In an existing building, you have retro commissioning. It's really looking at a system that in a building that was originally designed for the building but has never been adjusted, has never been looked at since the building was installed. We see a lot of what they call operational drift in buildings. Maybe you installed a chiller at a certain capacity, and then lighting was adjusted over the years. The heating system was replaced, and this is looking at how the building actually operates in current conditions and going through and testing equipment and realigning the building with what should be designed given current states. There's continuous commissioning, and that's implementing a rolling commissioning process, such as using a building management system or trending data to really keep track of implementations that have been made and continuously make improvements in a building. And then there's a recommissioning of a building. That's a building that's already been commissioning, and looking back at those original commissioning reports, recommissioning the building and getting the building back away from that operational drift back onto the original design for the building. So again, I'm not going to go into much detail on this slide because I already mentioned operational drift and design intent. But there's 2 good resources at the bottom of this webpage that I'd like to pay attention to. It's the California Commissioning Collaborative and the National Environmental Balancing Bureau. These are organizations that really provide standardization in the retro commissioning field. It gives you procedures and standards for how to conduct retro commissioning. The third level of energy audit is a level 3 energy audit, which really builds on the level 2. This is where you get into real capital-intensive projects. You really have capital-intensive projects, so not only is this identifying operation and maintenance issues, but it's also identifying low-cost, no-cost measures, measures of small payback, but also capital improvements such as system redesign, boiler replacements, basic items that aren't going to have necessarily a great positive payback. So how do we assess a building for energy efficiency? Well, the first thing we do is we compile any information we have regarding energy use. This is usually in the form of utility bills, and analyzing the energy use for the building over different time periods, looking at hourly or interval data if available, looking at energy usage per month, day, year, and then also benchmarking the building using software such as the EPA tools, Portfolio Manager, and Target Finder to see how your building performs to other buildings across the United States that would really fit into the same category, that would have the same size building, same occupancy hours, and adjusting, normalizing data so that we can compare buildings equitably. And then the third thing is really identifying patterns of usage. How does the building respond to outside temperatures? How is the building used? How does it respond to different occupancies in the building? And performing an energy audit and really going in depth to see what's going on in the building and how we can make improvements. So the first thing is benchmarking a building. The purpose of benchmarking a building is to quantitatively express how a building is performing relative to how it should be performing. Using tools such as Portfolio Manager, we're really going to see rate a building on a scale of 1 to 100, with 50 being average, and seeing if the building stacks up to its peers in its peer group, meaning buildings of similar size and operation. And then also show how a building benchmarked against itself, how it performs 1 year compared to the next or 1 month compared to the next. It's helpful to track energy usage over time for a building and look at, whether it's 2010 or 2011, how a building improved, how a building may have handled the heating season or cooling season or base period, and seeing how that can be improved from year to year. I just wanted to mention here, because this has been popping up a lot lately, I've heard a lot about, there's a BEPA ASTM standard. BEPA is the Building Energy Performance Assessment. And it's an ASTM standard E279711. And really this is an attempt to standardize the way that commercial buildings are benchmarked and rated for energy usage. And a lot of methodologies here are similar and are present in the Portfolio Manager and the other EPA software. The interesting thing here is that this is geared, designed by someone with a background in commercial real estate. And what's interesting is that a wider range of statistics are used to evaluate a building, including the 25th and 75th percentile. It's looking at a building and showing how a building will perform and how much it will cost to operate, not only under kind of normal or average conditions, but also in the coldest year, which may be the worst case scenario in a heating climate, and kind of in the warmest year, which may be the worst case scenario in a cooling climate. So to touch on the EPA tools that I've mentioned, there's two really: Target Finder, which we like to refer to as the quick and dirty way to assess a building. As an energy consultant, we'll use Target Finder a lot when we're first getting involved with a project. The calculations and the rating for between Target Finder and Portfolio Manager are very similar. They should be close to the same. The only difference is Target Finder is going to require a lot less inputs. It's not going to be so concerned with monthly data as it is with annual data. And when we're just getting involved with the building, we can upload our annual data, plug in some parameters such as occupancy, space type, and we can get a feel for how a building performs. If we have a building that only scores a 30 out of 100, we know that there's a lot of work to be done, and that the chance of having a successful energy conservation measure implementation program is going to be high. If the building's already scoring 74, 75, then we know that this building it's going to cost a good deal of money to improve that building even further, but it's also going to be a good candidate for programs like Energy Star certification or LEED existing buildings operation maintenance. Portfolio Manager, like I said, uses the same calculations. The big difference is Portfolio Manager is really, they're both free, but it's really set up to create an account and really track your buildings over time. If you're a building manager, property owner, or an engineer working on several buildings, you can put in all these buildings in the Portfolio Manager and look at them as your own portfolio. Compare one building to the next, and also keep track of update monthly utility bills every time that they're received from the utility company, and really track the progress. This is great for tracking progress over time. If you're implementing energy conservation measures, that you can track to see if progress was made. If you had a goal to meet a 4% energy reduction, this is a good way to track it. Just diagnose early whether the program is going successfully or not. Again, here the major difference between the two programs is Target Finder. Really is a one-time input. Once you leave the web page, it's gone, but it gives you a good indication of where a building stands, and Portfolio Manager is more of a long-term commitment in the sense that you're going to want to use it over the course of time and update it regularly. The importance of these software is to tell not only if your building is good or bad, but how much potential there is for further work in the building, or how close you are to meeting a goal, such as certification, such as in-house conservation goals, and also comparing buildings across your portfolio that may be similar to one or the other. The main data compilation that drives a lot of these calculations is referred to as the CBEC survey. It's a Commercial Building Energy Consumption Survey. This is very similar to the consensus survey that's sent out to every U.S. citizen every 4 years. The survey that's sent out to commercial buildings every 4 years, with the hopes of getting positive responses back, with people providing input as to how their buildings performed, different factors such as occupancy, operational hours, to feed this database that's continually growing of commercial buildings. Based on these building inputs, statistics are run, buildings are set up into peer groups. then like buildings are fit onto this curve that you see on your screen. So again, it's a 1 through 100 percentile rating, 50 being average, 75 being high performing, 1 being the worst, 100 being the best. It's important to know that also this is really geared towards commercial buildings. Buildings such as single-family homes, industrial buildings don't really fit in this category. There's a certain amount of eligible building types that are available for benchmarking. A lot of this is due to the sample sizes of the buildings that they've collected. Office is obviously the largest category where they have the most information about offices, but as you get into things like houses of worship and senior care facilities, that sample and that database gets smaller and smaller, providing less and less accurate information until you hit industrial facilities and other facilities that can't be properly benchmarked. Another trick to consider is that there are a lot of multi-use buildings that may only be 2 stories and have a bottom story that's retail, a top story that has office space. Portfolio manager defines the building type as the building that has at least 51, as a building space type that makes up at least 51% of the building. For most incentive programs, most state regulation, most city regulation, the proper way to benchmark these types of buildings is to actually assign different space types within portfolio manager. And you'd have a portion of the building classified as office area, part of it classified as retail area, and the general overall score would come from the dominant space type. So again, you see the curve from 1 to 100 here. The chart on the right with the red circle on it just shows the lead EBOM points that are available. Like I said before, 69 is required for lead EBOM, but there's additional credits available for buildings to score much higher than 69%. Once you hit 75%, your building would be eligible for Energy Star certification. So, as I mentioned, the Commercial Building Energy Consumption Survey. This was first conducted in 1979. So as of right now, there's over 30 years worth of data available. It's conducted every 4 years. Right now, the sample is still relatively small. It's 5,215. Data is not current. It's from 2003. 2007 has not been released. And portfolio managers come under criticism for not having the statistics to back this information up and to also update it with 2007 and now 2011 data. So it'll be interesting to see how we proceed in the future using this software. What's interesting is that a lot of the data from the 2003 CBEC survey has been extrapolated to show kind of what the makeup is of commercial buildings in the United States. According to the survey, there's about 4.9 million commercial buildings, 71.6 billion square feet. And importantly, about 50% of all energy usage is dedicated towards electricity, 32% natural gas, and 13% other forms like propane, oil, district heat, district steam. Okay, so here, if we start to categorize information by building type, underneath kind of the umbrella of commercial buildings, you'll see that office, mercantile, warehouse, and storage, and education are kind of the top 4, just based on square footage. I'm going to flip to the next slide right now. This is the same chart, but also but looking at things from an energy consumption perspective. So you'll see that at top you still have office as the dominant category, using the most amount of energy. You still have mercantile. But what's interesting is you have education, you have healthcare pop up, because they're intensity-wise use a lot of energy on a per square foot basis. They bump ahead of things like lodging, warehouse, and storage, and food service. If we look at energy consumption by building size, we'll see that kind of the highest energy users are the buildings that fall between 100 and 200,000 square feet. I can confirm that this is kind of where a lot of our work comes. It falls within 100,000, 200,000 square feet. These are kind of the office buildings that are not quite big enough for a large BMS system that monitors every point and doesn't have the capital, the financial capital to provide really kind of top-rate equipment and kind of sizes below that. You have a higher intensity, you have a lot of plug loads, you have kind of smaller equipment, there's limitations with equipment. This may be where you have a lot of split AC systems up in the Northeast where you don't have a high cooling load, so they may be using less efficient equipment. If we look at energy delivery breakdown by type, here's where we see where 55% of energy usage is used for electricity in commercial buildings, 32% natural gas, and then all other forms of heat make up a smaller fraction. If we break that down further, we can see kind of what pieces of that pie make up water heating, cooling, heating, computers, plug loads, office equipment, other components, and how electricity and natural gas are used within the building. What's interesting is the kind of trend in energy use intensity. So this is looking at site energy use intensity, which is energy used at the site on a per square foot basis. As you see towards the end of the 70s, early 1980s, there was an oil crisis, so natural gas declined sharply, and at the same time, electricity kind of stayed steady. Once you hit the mid-1990s, around 95, you'll see that it starts to go up. This is a result of technology. People started putting personal computers in every house. You have big screen TVs. You have a lot more electronics in every house. This is why there's a lot of focus on solar photovoltaic panels and other forms of renewable electricity as a form of energy. This is a lot to counteract kind of the increase in electricity energy associated with technology. So other places where CVEX information is used outside of the Energy Star certification in LEED certification systems, you'll also see a reference in Architecture 2030 goals, and also some of the federal standards that are coming out and some of the federal regulations. In some cases, especially working within eligible building types or buildings in special cases, you do have an opportunity to work with the CVEX data directly. We've had a couple projects, such as international projects that weren't in the United States, but we still wanted a relatively good benchmark to compare them to. One example is that we did a project in Bermuda where we really wanted to see how the building performed, but due to the size of Bermuda and the lack of a benchmarking or rating system, there really was no good comparison. The best way that we did it was we compared kind of outside dry bulb and wet bulb temperatures and found a relevant location that was similar to Bermuda. I believe for the purpose of that example, we used Savannah, Georgia, that was very similar. And we were able to plug in and assume that the building was in a similar climate, but really benchmark an international building and at least put it into perspective. It wouldn't be eligible for any type of certification, but at least put it into perspective how a building is rated on a scale of 1 to 100, and relatively if it's a good performing building or a poor performing building. Other buildings that fit into this category may be a campus-style building, a building where you don't have separate meters for each building, a building where the building may be fed off of a common chiller, or 3 buildings may be fed off of a common chiller or a common boiler. We have to kind of divide up that energy usage and see relatively how those buildings should be performing, even though there's not a specific data available. Here's just a website to show you kind of how to navigate and what the web page looks like for navigating the CVEX survey. You can actually go down and do a lot more level of clarity. If you're in New England, if you're in the Middle Atlantic, you can actually look at more of a regional census division as opposed to just a national number. If you're looking at a specific building, you can kind of pull apart and look at it on a more regional basis. You can break down an office building a little bit further, look at mixed use to the general category, and really define how well buildings performed according to your own kind of peer group that you decide. So again, these are the 2 kind of input screens that you'll see for Target Finder and Portfolio Manager. Really the statistical models that drive these 2 pieces of software really look at predicted energy versus actual energy. So in order to normalize data, there's each building is separated into a peer group based on kind of rough parameters of how many workers are in it, how many computers, the total floor area of the building, climate factors such as heating degree days and cooling degree days. And these, you'll see in that formula under predicted energy that a lot of these factors are multiplied by a coefficient, which weights them into that peer group as to how much of a factor floor area workers affects that peer group. So as an end result, your building gets assigned a predicted energy use intensity, and it's compared to actual energy use intensity based on your actual utility bills. So you're comparing how your building should be performing compared to other similar buildings that have been normalized to actual building conditions for your building. Here's an example of a project we worked on in Washington, D.C. I picked this project mostly because it's an all-electric building, it's a large building, and it's easy to see how to use the EPA tools. I use Target Finder only to show you guys how easy it was to put in annual energy consumption and basic building parameters to get kind of a target rating. Here you'll see that we put in the zip code. That was important for identifying climate data factors such as heating degree days and cooling degree days. We selected a space type as office. You'll see that there's just basic parameters such as gross floor area, operating hours, workers on main shift. We plug that in. On the next screen here, we select the target rating. So this tool is actually going to give us a design rating, which is, in this case, we'll actually put in the annual energy usage for the previous year for this building. The design rating is going to tell us kind of based on that input how the building would rate. And we could set a target rating of 90 to see kind of what a similar building, what achievements would need to be achieved in order to receive a score of a 90. So you'll see here we have the design column and then the target column. So our design here for this building is a 74, which is a really good building, very close to high performance. That shows us that we already qualify for LEED certification and that we're really close to achieving Energy Star status in a high performance building. That gives us that site energy use intensity number, which is really going to be a driver of these softwares. It's going to be the total amount of energy used at the site on a per square foot basis per year. Our target says that right now we're at 71%, and in order to have a building with a score of 90, we need to reduce energy consumption to a total site energy use intensity number of 53. So this can help define goals and allow us to see what we would need to do in order to achieve a higher rating than we already have. You'll see at the bottom too, we also have pollution emissions. So we're looking at CO2 and greenhouse gases emitting by your building and what could be emitted if we reduce energy consumption. For those of you who don't know too, electricity is one of the most expensive forms of energy. And part of the reason is because the amount of electricity that actually arrives at your building has lost about 70% of its power and energy content as it's traveled from the power plant and as it's been generated. So if you think of a typical power plant, if you guys have ever been in a power plant, there's a lot of kind of light and heat that's generated as a byproduct of the generation process. A lot of that light and heat is a form of energy that's lost from the generation of electricity. In addition to that, you have transmission losses as the electricity travels across wires and through transformers to your building. So what you're seeing at the building is really only about 30% of the actual electricity that was generated to get that power to you. The actual ratio is 3.3 to 1. This is important because when you're calculating emissions factors, it's important to look at the direct emissions factors, which would be kind of how much power you used at the building and how much greenhouse gases that would offset if you reduce that number, but also looking at how much power generation, how much greenhouse gas was emitted at the power generation facility. So there's a lot of factors that go into this. So we have, you'll see at the bottom right, you'll have direct emissions factors. So that's going to be a simple calculation that Portfolio Manager uses to kind of show what the greenhouse gas emissions are at your specific facility. And at the top left, you have the indirect emissions factors. So the country is broken down into different regions based on what type of power and the mix of power that goes to your building. In New York City, we have a lot of nuclear power. We may have some hydroelectric power. Or maybe out more towards the Midwest, you have a lot of coal power plants. Each one of those power plants is going to have a slightly different emissions factor. Coal is a lot dirtier form of energy. It's going to have a lot more greenhouse gases emitted as that coal is combusted at the facility to make electricity. and ultimately those indirect emissions factors are going to factor in to see how many greenhouse gases your building is responsible for. Here's just kind of a chart. It's from 99 to 2009, but showing the number of buildings that have kind of applied for the Energy Star label and received it. You'll see that in 1999 it was a very few number. That was when the program was still in its pilot phase, and it's kind of exponentially expanded throughout the years. It's really showing that energy efficiency has really become center stage in our built environment, and it's become an important factor for commercial buildings. So now that we've benchmarked a building, what do you do? How do we actually assess the building for energy efficiency? We know how our building performs, but what do we do about it? This is where we get into kind of the preliminary energy analysis. This is looking at your utility bills, looking at how much money you pay for electricity, for natural gas, for steam, for all the different utilities, recognizing if there's any demand reductions, any cost reductions that can be made, looking at things like base loads and trying to figure out how well the building responds to heating versus the cooling system. You know, here's just a kind of a screenshot of it's a typical Con Ed utility account online. Con Edison is the local utility for electricity in New York City. Essentially, this is a record of what a client's been billed for, both in units of energy as well as cost of the electricity and gas. A lot of utilities across the country may not have a website yet. They may still do paper billing. But essentially, it's collecting this information, looking at least 2 years' worth of data, and starting to analyze that data to see how our building performs. So once we take that data, this is data taken exactly from that Con Ed bill. This is only the previous year. The Con Ed bill showed us 2, but we deemed that there weren't any major outliers, and the previous year was the best year to use. We have electric use, we have electric demand, natural gas use, and the cost associated with each. The first step that we really did was we added heating degree data and cooling degree data. There's a lot of weather sources that we can obtain this information for, but essentially degree days are going to be an indicator of how much energy is required by a building in relation to outside temperature. In a lot of climates, a reference number of 65 is used, which means that it's assuming that 65 degrees outside temperature is really a balance point for your building. This can be adjusted. Say if you're in California or Miami, you have a lot of humidity. You may have to adjust this number. But based on a 65-degree reference temperature in this example, a heating degree day would be any day with an average temperature lower than 65. For every degree under 65 for the average temperature for that day would be considered a heating degree day. If we tally those up for every month, we can start to populate this chart. The same thing goes with cooling degree days. For every day with an average temperature over 65 degrees, we can tally up those degrees and get cooling degree days for every day and look at it from an annual perspective. Just to go back, this building was in Brooklyn, New York, so you will have a higher, as expected, a higher heating degree day number as a cooling degree day number. So for this year, as an annual total, we had 4,476 heating degree days in Brooklyn, 1,558 cooling degree days. So again, this is just showing you kind of other factors that we can look at. Once we have those initial data forms that we populated from the utility bills, we can start to look at energy usage on a per square foot basis, on a per dollar basis. We can see how much third-party supply versus delivery costs are if you're in an area that has disaggregated energy usage. And we can also start to define things such as baseload energy usage versus seasonal load. So here we are for that same building. We're looking at electricity usage. So this building did have quite a bit of electricity usage during the summer. This building, to give you guys a preview of the gas usage, is that this building actually has a gas absorption chiller that's responsible for doing heating as well as cooling, but it also has a significant amount of electric cooling involved. So looking at the shoulder season, so knowing that this is in a northeastern climate, where the predominant energy use is going to be kind of heating based on outside temperature, but there is going to be a cooling load associated with internal heat gains. We can determine a base load that looks at kind of the shoulder seasons, the November, the April to May, the periods where energy usage or electricity usage was the lowest. We know that these are going to be the months where the building did not respond to outside temperatures, because temperatures were right around that 65-degree mark. This is going to define our baseline period, so we draw that green line across, showing our electric baseline. And kind of all the energy that falls above that line is going to be weather-dependent energy usage. So you'll see between the months of May to September, we have a huge peak involved. This is really going to be the cooling usage associated with electricity. And during the winter months, we have increased electricity, probably due a lot. This happened to be a hospital building. They had a lot of exterior lighting. During the winter, you have a lot shorter days, the longer nights. Lights that are on photocells are left on longer. There's going to be increased ventilation associated with heating, and a little bit of spike in electricity, but there's a large spike during the warmer months for the cooling load. Looking at annual natural gas usage versus cost, you'll see that a lot of this natural gas usage was used for heating the building. So kind of where you see that red tie-dyed chart area. That's going to be kind of the area above our baseline for natural gas that was used for heating because it occurred in the cooler months. Kind of using October and June to determine our baseline, we see that kind of that 10,000 therms and below, that green line for every month, that's going to be a lot of just basic natural gas usage, a lot of domestic hot water usage. There's a hospital, so there's a lot of showers and baths being taken, a lot of hot water usage. There's 4 cafeterias in the specific building. So there's a relatively high natural gas baseline. Then also during the summer, you're going to see where those absorption chillers were driven to provide cooling for the building. So we also have a peak in the cooling. Doing a little bit further analysis, we know what the heating and cooling of both electric and gas is in this building. By doing an energy audit, we can collect inventory to look at how much lighting is used, pumps, fans. Kind of what's left is electric miscellaneous. This usually revolves around plug loads, various things, security systems, security cameras, things that are plugged in that are hard to that we don't have a great effect on, and that are hard to kind of classify and total up. We can leave with electric miscellaneous. So it's important to look at kind of from a general perspective the percentage of electricity used in the building versus natural gas. So on the left, you'll see electricity accounted for about 37% of total energy consumption, 63% for natural gas. If we take that same pie chart and look at it from a cost perspective, since electricity is a lot more expensive form of energy, especially in the Brooklyn area, electricity actually costs a lot more than gas and occupies about 67% of total energy costs for the building. This is important to consider when we're looking at things like lighting replacements, lighting and other electrical measures that we thought may not have a great payback because they make up such a large percentage of the cost of the building. We may want to check it out and see, even though we're only reducing a moderate amount of electricity, the cost can be substantial. Breaking up further, we can see that using the chart that's 2 slides back, you can see the breakout when we include domestic hot water, you have gas, pumps, lighting, cooling electric, heating electric. I'm looking at it again from an energy use versus an energy cost perspective. So if we were to make some improvements on heating, we would think that we'd have a big percentage of cost savings because heating occupies 25%. But from a cost perspective, total heating usage for gas is only about 13% of the total energy bill. Another way to really look and get more insight about your building and how well it responds to outside temperature is to actually plot those heating degree days and cooling degree days that we mentioned. For this building, on the cooling degree day side, you can plot cooling degree days against the actual electric usage for the building. We see that during kind of the winter months, there are no cooling degree days, so most of the electric usage is going to be based on heat required for the building and also the base loads, plug loads, that electric miscellaneous category lighting. What's interesting is that we see that The building actually responds appropriately in August, which would be the hottest month for this year. And there's an accurate amount of energy consumption that's used, which means that the building is actually sized pretty correctly, most likely, and the building kind of system peaked and used most energy at the time when outside temperatures were the warmest. What's interesting is if you follow that arrow from number 2 up, I do a little purple kind of trapezoid. We see that there's a big jump in electricity usage as the building reaches into the summer. This usually tells us that there's some type of control issue, that maybe the building's not reset in outside temperatures. Maybe kind of cooling was initiated before it was necessary. Maybe the building doesn't use economizers. But there is some issue there that we should explore further. Looking over at natural gas usage, in this case, we would normally look at heating degree days only. Because this building just happened to use an absorption chiller, which uses natural gas for both heating and cooling. We actually combined our cooling degree days and heating degree days to just look at kind of general degree days, which is kind of energy content expected to be used for the building based on outside temperatures. What's interesting here is we have the same kind of perhaps maybe controlled issues starting in March and traveling down to May, where energy consumption really kind of spikes higher than expected based on outside temperatures. This just kind of gives us a visual clue to explore this issue further and see how well the building's doing, and maybe there's a controlled issue to explore that. Breaking everything down back to that site energy use intensity, looking at a kBTU per square foot number, converting natural gas and electricity both to kBTU so that we have common units. We see that really natural gas is the majority of the usage, and it's going to be the most weather dependent when compared to electricity, which is exactly what we'd expect for this building. We also know that the total site energy use intensity, if we add all the months, is about 131.4. But once we plug it into Portfolio Manager, we realize that it's not that bad of a performing building. Just before I go on to kind of further energy analysis, I just want to point out we can also use building analysis really to determine if there's any opportunities for reducing costs through energy purchasing and procurement. There's a lot of third-party suppliers in areas where energy usage has been disaggregated, meaning that you can shop around for a third-party supplier. A lot of that information is published, and you can look to see kind of what the average rate is that a building pays for in your area of similar size, and determining if the building pays a high or low rate based on the average. We also have things that we can analyze, such as power purchase agreements. This is very common with cogeneration and also solar power, photovoltaic technology, where you're actually generating electricity on the site, and then it's being sold to you by a third-party supplier. We have leases. In some areas, you actually lease roof space for things such as solar photovoltaic panels and also cogeneration. We have performance contracting, consortiums, and demand reduction. So to take kind of the preliminary energy use analysis one step further, we know kind of what to look for. We identified that there may be some control issues. We see kind of what the heating and cooling issues are in the building and what's expected of the building. We know the capacity is probably okay because cooling degree days and heating degree days peak at the right times with energy consumption. And what we can go in the field visit now, kind of limit our scope and really focus on some issues within the building. It's great to go in and take single measurements, such as combustion efficiency testing, taking shots of the infrared camera to look at insulation issues and how thorough insulation is in the building, and doing a preliminary walkthrough. But an important factor to consider with energy usage is time. Data loggers allow us to log different performance conditions or different conditions and parameters over time in the building, things like temperature, relative humidity. We can look at event changes such as lights on or off. We can look at light sensitivity, how many lumens per square foot were produced by a lighting fixture in a certain area, and also look at other factors we might not be able to. We just happen to go into a building on any given day. We only see a snapshot, and we might not have an opportunity to see these buildings over time and how a building responds throughout the day, continuing on into the night, weekdays versus Where data loggers used, they can be used pretty much anywhere. There's a lot of data loggers, and we personally use a lot of data loggers for renewable energy systems monitoring, rooftop HVAC systems monitoring, weather monitoring, time of use monitoring. This is really important when we want to look at things. A lot of times we have lighting. No one really knows how it's controlled. It just turns on and off. We can put time of use logging in. It actually records event changes, whether a light fixture was on or off. And lets us know, kind of figure out what the actual schedule of the lighting is, so we can make improvements. And we can install motor on-off data loggers to tell us when a motor was turned on versus when it was off. We can look at boiler chiller performance monitoring, so we can install ultrasonic flow meters and actually look at chill water flow through a pipe, while also monitoring supply temperature, return temperature, power used by an electric chiller, and also power monitoring and IEQ monitoring. We can look at things like CO sensors, CO2 sensors, to tell us if it's a good opportunity for demand controlled ventilation, and also kind of get creative with it and use it for things such as determining occupancy. These are kind of some of the common data loggers that we see in the field. We'll go through a bunch of different types, but these are really a lot of portable data loggers. This includes having kind of wireless data, wireless sensors that report back to a central hub that allows us to have a common data logger for multiple sensors and access that information. Really not tie up people with cords and have sensors placed throughout the buildings, and then come in and collect data, report it to a wireless network, or report it to a computer, and view that information on screen. Some of the sensors that we use that we can also monitor at different points. We can look at things like temperature, relative humidity, CO2, differential pressure, energy and power is a big factor, demand. We can monitor power factor. Look at things like state changes, light on, motor on, off. There's a bunch of other uses. Things like weather stations can be set up to look at outside temperature. In buildings, we can look at enthalpy inside the building versus outside the building. We can look at how temperature and humidity outside the building affect the building inside. And we can also hook it up to other equipment that receives different signals and really record an unlimited amount of data. These are probably the most common sensors that we use. They're integrated sensor models. These are basically limited temperature and humidity, or also time of use, such as lights and motors. These are just a simple install. We use a computer to stick them out in the field. They'll record at different intervals, temperature and relative humidity. It really give us feedback into how a building's performing, or how a specific system is performing. We have external sensor models, kind of sensors that have different inputs, maybe 4 channels worth of inputs that we can hook up. We can look at things like demand monitoring, power monitoring, power factor, and send it to a central data logger to log data at different intervals and read that information later. We also have web-based monitoring systems where, like I mentioned before, we can send a wireless signal from different sensors to a central hub. You'll see in this picture here we have the U30 hub. It's a hobo device that connected to a computer can actually send that data out through the web, and we can access from anywhere in an office. So from an energy consultant perspective, this is great. We can see what a building's what's happening in the building, kind of diagnose it without leaving the office. We can see if our deployment of sensors is actually going well, or if we have any errors, and we can go out into the field and correct it. We also have a lot of information available at our hands without having to go back into the field. Again, here's wireless data loggers. So this is going to be data loggers that are really picking up, you have sensors that pick up different signals, send them to a data logger, reports back to a computer. We have weather stations. These would be great to install on a building. We can put it on a roof. In a lot of areas such as New York City, we have microclimates that occur. You have buildings that may be surrounded by other tall buildings that block wind. Maybe the temperature and relative humidity for that area is different enough from the local weather station that it actually makes an impact on your energy analysis and calculations. Then also there's a powerful software that comes with the HoboWare. It's called. It comes with some of the Hobo equipment. This lets you analyze a lot of the data right there through the software. If you're going out in the field, you can hook up a data logger to your computer and start analyzing that data, and then redeploy the temperature sensor, the data logger. You can also export the CSV file and edit through Microsoft Excel. Here are just some of the kind of input screens. With different loggers, we can kind of set what parameters we're looking for, what we want it to log, the time intervals that it can log. Here's just another display. Kind of once we plot things out, we can change the plot lines. We can look at things on time. We can look at two different events and how they interacted with each other. And it's important, really data logging can be used to kind of verify what we thought were existing conditions and how we broke down energy usage. But we can also use it to strengthen recommendations for energy conservation measures. Most commonly, we can verify kind of scheduled runtime of equipment, temperature, set points, relative humidity, lighting levels, outside air temperature, humidity. The U10-001 data loggers, we've used these specifically for deploying. We had one building. They had 4 cafeterias, one on each of the first 4 floors of the building. There were constant complaints that the 4th floor dining area kind of had higher temperatures, and people were complaining that it was hot. Building management kind of checked at different time intervals and couldn't find any anomalies. They didn't think the temperature was very hot. So we were hired to go in. We deployed some of these data loggers in each cafeteria. We see that the first 3 floors had average temperatures that were very similar to each other. They responded similarly. The 4th floor was obviously much higher than the other floors. Going back and re-examining the equipment that's installed in the building, we know that the 4th floor did have an anomaly and that it was much higher than expected. We concluded after a further inspection that there was actually an air handler serving that floor that had a malfunctioned hot water valve on it. It was sending a lot more hot water than necessary through the air handler to the floor. The U9002 data loggers, we installed these in office space where the lighting controls are very vague. No one kind of knew how they were controlled. There was a sensitivity dial. It wasn't really clear when lights turned on or lights turned off. So we installed simple light on, light off data loggers. Here's kind of a chart showing our analysis. Kind of the blue box surrounds kind of the existing conditions. So on a typical weekday, you'll see that lights turn on at 6 a.m. and off at around 9 p.m. Based on occupancy schedule, this is unnecessary in the office since the very first person in the office comes in at 8 a.m. and the last person leaves at 7. So doing a further analysis, we knew that how much energy the building was using for lighting in that space and how much they should be using based on that adjusted schedule. We can compute total power from the light fixtures times the hours of reduced runtime and calculate a total kWh savings for that office space. The U12008 data loggers we used to really evaluate, we had a building that had air code condensing boilers installed that were chosen specifically for high efficiency, yet utility bills were still extremely high. So we went in there to test out the building and see how we could use data loggers and kind of verify whether the unit was performing as expected or not as expected. We placed temperature sensors at the boiler header, supply and return, the boiler or the building would return, and also the return from the domestic hot water heat exchangers. So looking at this data that was collected, we saw that the supply temperature and return temperature of the boiler really weren't different from each other. With a condensing boiler, you really want return temperature coming back at less than 130 degrees. In this case, we didn't have a big delta T between the two temperatures. So the boilers really weren't condensing as they were supposed to, which indicated to us that we really need to make an improvement to reduce the return water temperature. So here, looking at the same chart, the previous one just showed kind of the outside temperature and how the building, how supply temperatures also responded to outside air temperature. In verifying the outside temperatures did call for heating. Here we looked at just kind of those conditions themselves, in part load conditions and full load conditions alike, that the building supply temperature didn't vary too much. If it did, it didn't vary from the return water temperature, and that return water temperature very rarely came back less than 130 degrees, which meant that the boiler was never going into condensing mode. This building, the heating also did have a domestic hot water heat exchanger to it. It was a very small capacity. It wasn't enough to drop the temperatures lower than we anticipated. So ultimately, we could reduce supply temperatures and allow for return temperatures to come back a little bit lower so that the unit was in condensing mode. This is a similar setup in a different building. We use the U12-006 data loggers. We use the building heating supply, building heating return, and mixed domestic hot water. For this, what we saw was important in this chart, only kind of showing the supply water temperature. As we noticed right away that the supply water temperature was always right around 150. It wasn't adjusting too much based on outside temperature. Generally, it was staying the same. This building did have outdoor air reset, and this boiler should have adjusted based on outside air temperature. So we saw that the outdoor reset for the building wasn't always functioning, and whether there were periods of high domestic hot water demand or low domestic hot water demand, return temperature was never dropping below 130. The Hobo model U12-012, this is the ability to measure small changes in light levels. There's a resolution of 0.7 to 0.8 lumens per square foot. It's really highly dependent on the placement of the sensor. In the first example, we sorted it, and this is actually a high-rise building where we installed it in the stairwell location. We had already recommended in this building went forward with the implementation of bi-level lighting sensors. So on the left-hand side of the chart, you can see that kind of over 50% of the time the building was at these sensors picked up the lighting was at a low level, whereas the rest of the time the building was at a higher level on the right-hand side of the chart. Based on lumens per square foot number. There's a clear distinction between on and off. These were in stairwells where there wasn't window, there wasn't light allowed through the window. The only lighting in these areas was from the bi-level sensors. You could see that they were actually working, that most of the time these bi-level sensors were in kind of the low light mode, and then were responding to occupancy and kicking up to the high level mode when occupancy was high. So we saw that data is captured instantaneously every 2.5 minutes. A lot of these sensors had, a lot of these light fixtures had time delays on them. So if no one was in the hallway for a period of 5 minutes, the lights would shut off. And then as soon as someone entered the building, the light would remain on for 10 to 15 minutes. So to back up, so to show you another example where we use the same sensor, we also installed these in the corridor of the same building. This building, the corridor did have windows that had doors with glass on it. These light sensors in the hallway picked up lighting other than the overhead lights that we were trying to monitor. We'll see that the intensity, although the sensor gave us a good reading and there was a good sensitivity, we saw that there's a very small difference between on and off. That, during the daytime when light was shining through the window and elevators were going up and down that projected some light into the space, there was a very small difference between when lights were on and when lights were off. This led us to assume that light fixtures were not turned off fully when unoccupied, that a lot of the building lighting was still remaining on, and that there was significant light coming in from other sources that we may not have needed as many lights to be on. That the occupancy sensors and the daylighting sensors in that space could be adjusted to allow to turn off the fixtures more based on ambient light. One important example that I want to express to you guys is that we can get creative with logging data, combining it with single point measurements and also using other equipment. To look at things like chiller efficiency, we can install an ultrasonic flow meter on the chill water supply pipe, so we actually know how much water flow is going through the pipe. Looking at also the temperature of that water and the temperature of the return chill water. We know how much heat energy or cooling energy is being shed in the building. And also monitoring electricity at the electric panel. We know we can evaluate the efficiency of chiller at different conditions. So when the chiller was at peak conditions, when it was using the most electricity, we know how much electricity was required for capacity, for peak capacity. And we also know part load conditions based on supply and return temperatures and looking at the volume of that chill water flow and how much electricity was required by the chiller. Kind of two important standards that you'll see pop up in every rating software and also throughout the commercial building world in the form of building codes and energy efficiency standards. We have ASHRAE standard 90.1. This is used for a lot of calculations in both LEED for new construction and existing buildings. In new construction, it helps you determine a baseline. When you have an engineer designing a building, they're going to use local building codes and some of these ASHRAE standards to determine kind of what the minimal amount of insulation is required for that building to provide your baseline case and meet local codes. Using the same calculations, they can see and kind of work backwards at what insulation levels are required and also kind of what materials get you to that insulation level. Same thing goes for glazing on windows. It's figuring out how to calculate the glazing for a window, including the frame and the glass. And also doing some calculations to figure out power density of lighting, knowing how many lumens per square foot or wattage per square foot is necessary for different space types and minimizing the energy used by meeting the minimum requirements of that standard without overshooting the goal. ASHRAE standard 62.1 references mostly to ventilation or entirely to ventilation. What's interesting is that this standard allows us to increase CFM. It helps us keep a building and its occupants healthy by introducing more outside air. But it also allows us to adjust outside air for demand-controlled ventilation, reducing outside air to a minimum when the building is not occupied and ramping it up based on occupancy in the building. We also have a whole building design guide, which isn't as common. I'll talk about it in a second, but we really put this on here because we started seeing some federal projects that came through. The whole building design guide is a collaboration between the private and public sector. It mentions everything from project management down to some of the energy efficiency calculations. And then lastly, the International Performance Measurement and Verification Protocol. So this is a standard that's big, especially in the data kind of logging and trending world. And now that we're getting into a lot of projects that have commissioning, retro-commissioning, implementation aspects of it, as well as kind of performance standards, meeting goals for incentive programs, meeting goals for regulation. It's standardizing the way that you actually measure and collect data and how to verify that a system's performing as it should. So again, this is ASHRAE standard 90.1. This is going to give you calculations to determine kind of the minimum requirements for energy efficiency in buildings. Each iteration is kind of adapted slowly by local building codes. You have ASHRAE 90.1 2004 and ASHRAE 90.1 2007 that are both being referenced in different building codes in the tri-state region, New York City, New Jersey, Connecticut. This helps determine minimum energy requirements for existing buildings, new systems within buildings, in different scenarios of the building. It's really helpful once you get into the energy modeling phase and actually trying to show different calculations for energy efficiency compared to kind of baseline conditions and what the minimum standard must be met in terms of supplying enough power and enough light from space, heating, cooling, and ventilation. Again, this is just another little bit deeper explanation of ASHRAE 90.1. You have Appendix G contained within ASHRAE 90.1 is really going to focus on modeling for the building. This is important for lead new construction when you don't have an existing building. A lot of lead rating systems and other similar systems, local regulation, incentive programs are going to require you to kind of model a baseline building. So it's taking the general design of your building, accounting for kind of the minimum energy efficient scenario, and then based on how well you can improve over that minimum scenario, there can be incentives such as credits in the certification program or financial incentives through a local program. 62.1, as I mentioned, really focuses on ventilation. Buildings, in order to get LEED certification, must meet ASHRAE standard 62.1. This is factored into a lot of building codes now. Essentially, it's providing minimum ventilation rates for unoccupied spaces on a per square foot level, and increasing those minimum ventilation rates as you have occupancy in a building. Again, here's the whole building design guide. This is a reference that I'm putting up there. A lot because we're seeing it starting to be referenced in federal projects. We have GSA projects that have referenced this. It's put on the National Institute of Building Science. It addresses everything from the team approach and how to get an architect and engineer on board, how to properly manage kind of the staff and the general contracting that goes into a building, as well as addressing kind of simple and most common energy conservation measures, and taking energy efficiency from a holistic point of view. This is just to give you an idea. There's different categories within the whole building design guide. There's a lot of overview. You can go through the overview and kind of explore. It's pretty neat how it addresses project management from a building, kind of a construction trades perspective. IPMVP, this is the International Performance and Measurement Verification Protocol. This is really a best practices technique for kind of how to monitor energy usage, how to log data, how to verify results. So this covers renewable projects, energy efficiency, water efficiency projects. I was going to tell you the correct ways and the best practice ways to look at things like flow rates, how to deploy instrumentation for how long instrumentation should be deployed. Now to discuss kind of energy modeling. There's a lot of various methodologies associated with energy modeling. As you go across the country, you see different kind of modeling softwares and modeling approaches. A lot of different incentive programs and regulations kind of adopt specific software, but in general, the idea is that you're going to take typical building conditions and create a statistical model. Look at kind of hourly weather data and see how that building responds and how the loads in that building responds on an hourly basis. Things how schedules for occupancy affect energy use in the building, how the building's controlled, kind of what resets are built into the control system, how the building responds to actual weather data. You can plug in things like energy rates and also use it for a way to kind of show in an existing building kind of what the existing conditions are, and also tweak measures such as tweak inputs such as increasing the efficiency of a boiler and seeing how an increased efficiency in the boiler and thermal efficiency affects the overall energy consumption of the building, how maybe a system redesign affects the energy consumption in the building. Kind of the most common energy modeling programs out there that do hourly load calculations that we're aware of and that we're familiar with is Blast, Carrier, HAP, the DO2, Energy Plus, eQuest, TrainTrace 700. In our company, we use eQuest probably the most. We find that it's generally the most accepted software for a lot of regulatory agencies and a lot of incentive programs, especially in the Northeast. It performs 8,760 iterations of calculations. That's how many hours are in a year. So it's calculating building loads and scheduling every hour of a typical year in the building. It accounts for interactions between building systems, so it accounts for the lighting load in the building. and how that affects the cooling system, the heating system, the ventilation. You can import and customize part load performance curves. So you can call it specific fans and change the fan curves. You can change how the performance curves of a boiler, of a chiller, and get extremely detailed to see how the different measures affect a building. And also calculate things such as solar heat gains based on the location. Looks at kind of the typical weather data for the typical year. Solar heat gains, infiltration, and also kind of the scheduling, how many people go into the building and the internal heat gain attributed to those people. So again, our company primarily uses eQuest for commercial modeling and lead projects. It's based on the DO 2.2 simulation engine. This is a free software. We particularly like it because it's not associated with any, it's not branded with any company name. It's the Department of Energy engine behind it. And it's really easy to use. There's a lot of training opportunities. We feel comfortable with the amount of inputs that you need to get an accurate model. So a lot of the standards that I mentioned, ASHRAE 90.1, you have ASHRAE standard 62.1. A lot of those standards are factored into eQuest. It makes a lot of assumptions by itself. It's your job to change those and kind of critique the model and make sure that you're customizing it to how your building actually performs. You can customize a lot of things, like I said, performance curves, adjust scheduling. Scheduling is important, and everything that would affect the building on an hourly basis. Energy modeling has really become an art. So the energy model is only as good as the energy modeler. Using things like methods of data collection and trending data can help us make more accurate inputs to input into the eQuest software, which enhance our outputs and give us better recommendations to make to a client and to be more accurate with our predictions. This is just to show you a screenshot. So one easy thing to do with a building that has multiple floors that are identical is you can make one typical floor and kind of extrude it up and copy that floor. So it's relatively easy to set up a building geometrically. The model iterations are fast. If you change parameters, it's easy to run. You get a new calculation. And it literally runs hundreds of iterations for a building design, looking at hourly analysis for an entire year. To give you an idea on the level of detail that this software has, we can go in and pick specific zones. We can assign equipment load for that zone. We can adjust the sensible output, equipment sensible heat output. If we're talking about maybe a commercial building that has a lot of process equipment, has a server room, we can go in and plug out specifics about what equipment's in there and how much heat is giving off to the space. We can go in, you can go in and choose kind of generic envelope constructions, roof constructions, wall constructions. It'll automatically calculate kind of the thickness, the conductivity, the density, and the R value of those spaces. We can go in and see what happens if we, increase insulation by 3 inches, if we put a different color roof material on, if we make a reflective roof, how that affects solar heat gain in the building, and how it affects overall energy consumption. What's neat is I like to think of this as kind of it has its own like BMS screen in here. It gives you a graphical view of the different components of the system. We can go in, if some of our outputs aren't as expected, we can go in and pick what system we think are affecting those outputs. We can call out specific chillers. We can look at it graphically just like you would do a BMS system and make adjustments without having to scroll through kind of an Excel spreadsheet type screen. That last slide was for kind of showing the water side interface. This is more on the air side interface. So if we go back one side, we'll see that there were kind of you see chillers, you see a chill water loop, you see some of the piping, coils, cooling tower. Looking at the air side, we see more of the chill water coil, supply fan. We see more what's going on inside of what would be like an air handling unit. We can look at different zones and see what equipment we would assign to that zone and really change and add control logic similar to what we would do in a real building in a BMS system. So some of the outputs that we might see is here. It would tell you kind of what your energy usage is. So in ECRETS, what we would do is we'd model the building as it is, compare it to kind of typical, if we have energy bills available, we kind of adjust parameters so we know we can kind of true up the building to actual conditions. But we also have a breakdown here that show us. So using our energy analysis we did before based on utility bills, we can look here and get a general feel for what the baseline should be, how much lighting is used in the building, how much heating versus cooling. Looking at it again on a per month basis, we see how that energy consumption breaks down between area lighting, pumps and auxiliary, ventilation fans, heating, cooling. Here's the same information in pie chart form. So if you remember back to when we did the energy bill analysis, we broke everything down just based on general assumptions looking at the utility bills. Here we can compare and see what happens when we plug the actual equipment that was in the building and put in some of the actual operating conditions, how our model compares to real life. So now I'd just like to talk about, we're wrapping up for probably the next 10 minutes, but we'll go through some of these case studies and then open up the presentation to some questions. Here's a building that I recently completed in August. It's about 300,000 square foot office building in New York City. We were hard to really do an ASHRAE Level 2 energy audit. So we went into this building, kind of evaluated how the building performed. We came up with a benchmark score for the building, and then also made some recommendations. So some of the recommendations we made, and these are just to highlight kind of real common ECMs, energy conservation measures that we've been seeing in commercial buildings. In this particular building, there was kind of a warm-up and cool-down period for the building. The air handlers kicked on. Were scheduled to kick on about 2 hours before occupancy and stayed on for 2 hours after occupancy. The occupancy being kind of the ultimate time when the first employee enters and the last employee leaves during the day. One of the things that we noticed that although this is a good thing, the air handler was kicking on to kind of pre-cool or preheat the building, that it was also operating the outside air damper. When there was no occupancy in the building, ASHRAE 62.1 allows us to adjust outside air and actually shut it off or go down to a minimum when there's no occupancy. So this air damper didn't actually need to be operated until the first person enters the building. So knowing that this building enforces a strict schedule, we could actually schedule that outside air damper to operate based on occupancy while keeping the air handler turning on and turning off for kind of a pre-warm-up and a pre-cool down period. This is much more efficient because you're no longer bringing outside air that needs to be heated or cooled. There is still an economizer override, so if it was efficient and cost-effective to bring in kind of cooler air into the building versus using the cooling coil, the unit still would, but generally the outside air damper is kept closed until the periods of occupancy. Likewise, we could install data loggers on. The toilet exhaust fan was hooked up to the BMS system, but no one was really sure how it was controlled or if it was actually turning on or off at night. There's a schedule inputted in there that was kind of grayed out. So we were there during the day. We couldn't observe it at night. We installed a motor on off hobo data loggers. We were able to see that the exhaust fan actually doesn't turn off. It remains on 24/7. So this building could hire someone to come in, the BMS controls contractor, to actually adjust the schedule and shut off the exhaust fan, actually in accordance with the outside air damper, so that it only comes on when there's actually occupancy in the building. Another ECM that we found in this building was that this building actually had a free cooling coil. So on days when there were only kind of peak load or part load conditions, the chill water coil wasn't used, so the chiller wasn't used. The condenser water, there was a condenser water loop that was used using the cooling towers. What conditions were required. During this part load, there were a lot of floors that didn't need this condenser water, but there was no way to isolate these floors. We could actually install electronic actuated condenser water valves. Essentially what this did was when that building was kind of working in economizer mode, if there were floors that didn't need that condenser water, we could actually bypass the floor, which reduced the pressure on the supply pump for this building. It could actually ramp down the supply pump VFD. Again, so this floor had an air handling unit on each floor. Depending on the size of the floor and the use of the floor, there were 4 to 8 compressors on each floor that were operated based on the control system using control logic. The stage on compressors based on a timer. So if a floor required cooling, kind of the first compressor would kick on for a minute, and then the second compressor would kick on, the third compressor would kick on, the fourth compressor would kick on, all the way up until the cooling condition was actually met in the building. What was happening was that 1 minute wasn't enough time, that when one compressor kicked on, that inevitably a second and a third and a fourth compressor would kick on, and eventually the units would freeze up, the building wouldn't be cooled, and the compressors would freeze up. What we did was we changed control logic. So these compressors were actually staged based on supply temperatures, and kind of one compressor was left on for so many minutes, and if conditions still weren't met, then the second one kicked on. This helped with energy efficiency in the sense that it actually cooled the building. It prevented the units from freezing up, and it was a logical way to meet space conditions. The original air handling units had constant speed supply fans. So what happened was that there were VAV boxes in each space. These VAV boxes, as they closed, just built up pressure in the supply duct. And the supply fan was just forced to ride its curve. There was no VFD to ramp down the speed of that fan. So this building had to install new air handling units. Since the old ones are about 30 years old anyway. Along with these new air handling units, they also installed VFDs and also put in static pressure reset. So as VFD boxes closed, the static pressure built up in the supply ductwork. The VFD on the supply fan was allowed to ramp down, saving on energy usage, fan energy usage. This building also had a 30-year-old 1,900-ton chiller, sized for 1980s lighting design modes. Essentially, this building has undergone many renovations on the lighting side. In the 1980s, it was all T12 bulbs with magnetic ballast. They give off a lot of heat to the space. Since then, a lot of the lighting has been replaced with T8 and T5 bulbs, compact fluorescents instead of incandescent, which really reduced the cooling load substantially. The unit was already oversized. So this normally wouldn't have been cost effective, except for the chiller was already 30 years old and needed replacement. But by evaluating and kind of modeling the current conditions, we could recommend that they resize the chillers for 1,100 tons at peak load as opposed to 1,900. Here's another building just to show you kind of a different climate. This is just done about 2 months ago down in Miami. This is a medical office building. In Miami, it was a different scenario. It was cooling dominated. There was cooling used throughout the year, almost no heating. We had a really high relative humidity. This building is only about 60,000 square feet. But essentially, the major issue in this building was that there was an outdated pneumatic system that had actually been decommissioned. So the VAV boxes, air handling units, and also outside air dampers and chilled water valves were all operated off pneumatics that had been disabled. In order to meet comfort conditions in the space, the building manager actually had to run around and adjust VAV dampers, chill water valves, outside air dampers, completely manually, either by wedging cardboard or a stick to hold the position of a valve or a damper. And really a lot of heat and humidity was a lot in the building that shouldn't have been. Our recommendation was to upgrade the BMS system to accommodate DBC controls, and then also put in electronic actuated valves at each of those points to allow them to actually have control over the system and actually modulate the system based on building loads and the cooling loads based on outside air temperature and inside air temperature conditions. This building also had a primary loop chiller system. So it had one chiller on the roof that served the entire building. Chill water was piped directly to the building and back to this chiller. Because of this, we couldn't recommend, so the way that this chiller was set up was that each unit had a three-way valve, and one of the main issues was that since these three-way chill water valves were no longer being pneumatically actuated, whatever position they happened to be stuck in determined how much chill water was allowed to flow through the chill water coil. We recommended that they upgrade almost all of the three-way valves to two-way valves, which would allow them to install VFD, a variable frequency drive, on the chill water pipe, on the supply pump. However, we ran into an issue where the chiller had to maintain minimal flow. We were lucky in respect that this building actually had one area that had a 24-hour occupancy. We left three-way valves there so that there was constant flow through that section, which met the minimum flow requirements for the chiller and also allowed us to modulate the amount of chill water that the rest of the unit saw throughout the building. Again, this building didn't have static pressure reset. When VAV boxes were closed or when they were stuck closed in the case throughout this building, static pressure was constantly built up in the supply duct, and the supply fans were working a lot harder than they needed to. We could add VFDs to these supply fans. It was a retrofit, and actually controlled them based on static pressure reset, which allowed the fans to kind of ramp down, and the motor that controlled the fans to ramp down and save energy usage, fan energy usage with respect to static pressure. The non-functioning outside air damper, many of these outside air dampers were stuck in the open position, which is the air handling unit was essentially pulling outside air at all hours of the day, even when it was 95 degrees out and 65, 70% relative humidity. By installing electronic actuators at these dampers, we could actually limit the amount of outside air that came into the building. The third example I'll just run through real quick because I know we're running out of time. This is the town hall in Connecticut. It was about 85,600 square feet. This is actually a gut rehab, so it was an existing building, but it was going over major renovations. Since the baseline model, if we looked at the building as it wasn't going to be really representative of what we needed to compare it to. We needed to make a model. Essentially, we're making so many changes in the building that this baseline is no longer relevant. We had to make a model, kind of see if we installed kind of the typical standard equipment, how the building would be performing compared to if we installed all high-efficiency equipment. So here's how the building was modeled through eQuest. Kind of the green layer, just visually, is the below-grade levels. We had to add the right amount of glazing, so the right amount and size of windows. Again, eQuest runs 8,760 hours per year, so it's an hourly simulation. So looking at our ASH rate standard 90.1 that told us minimum energy efficiency conditions, that was a baseline case. This is if we replaced all equipment as was. And then comparing that to putting in a high-efficiency boiler, high-efficiency chiller, installing energy recovery ventilators, and also installing demand-controlled ventilation. So I'm just going to kind of go through these quick. This is just a summary. These are kind of the existing conditions. There was an existing roof that was upgraded to have a higher insulation value. There were VFDs installed, energy recovery, new boiler, new chiller. Kind of looking at the baseline case, so that was kind of our minimal design based on ASH rate 90.1 compared to kind of the high efficiency recommendation that we recommended. We see that just looking at these two pie charts, the space heating was really reduced as a percentage from 28 to 13%. Ventilation was actually increased in this building because we used energy recovery ventilators, but those ERVs allowed us to reduce the load of space cooling from 14 to 7% and space heating from 28 to 13%. Looking at it from a cost perspective, we can see that a few categories like pumping and fan energy actually increased, but the amount that we were able to reduce heating and cooling more than made up for it from a cost perspective. Overall, this building had a net savings. We're saving energy of about 42% site energy savings, 22% cost energy savings over the modeled baseline conditions. So just kind of go through a couple of ECMs real quick. ECM number one is a lot of buildings that we see, and again, these are the kind of the most common ECMs that we've seen lately, and that you'll see as you come across commercial buildings, and more specifically as you get into larger and larger buildings. Adding reset control of any kind to different systems is generally positive if it's set up right. Looking at things like outside air temperature, pressure differential, return either hot water or chill water temperatures or air temperatures. We can reset a system, so it's actually looking at and obtaining feedback from different parameters within the building and adjusting supply settings based on that. We have ECM number two, which is just a generic adding VFDs when they make sense to hot water, chill water, or condenser water loops. Many times there's a lot of pumps and motors that are overworked when they don't need to be. So looking at if there's a way to reduce that fan or pump energy by installing VFDs and whether or not it's cost effective. Operating outside air dampers based on occupancy and not on AHU schedule. This goes for both supply, outside air, and exhaust air. This is operating based on occupancy. When there's no one in the building, there really doesn't need to be ventilation. If there is ventilation, it needs to be very minimal. We can operate outside air really only when the building's occupied. And this allows us to save energy during those non-occupied hours at night and on the weekends, which a lot of buildings don't think about it or don't have incorporated into their control logic. Bi-level lighting fixtures, this is big, especially when you get a high-rise when there's very few people that take the stairs. Building codes require that you have a certain lighting level present at all times in the stairwell. A lot of times this is the power density associated to the amount of watts per square foot of this lighting is a lot more than it needs to be. We can install fixtures that dim down to a minimal code requirement when there's no occupancy, and then brighten up to comfortable lighting conditions when someone enters the stairwell. We mentioned this before, but a lot of buildings, especially if they're 20, 30 years old, that have chillers that are original to the building still, they're usually sized for design load that was current at the time of the building, but a lot of changes and a lot of improvements in other technology allows us to reduce the size of a lot of this equipment. This goes for both heating and cooling equipment. Again, adding VFDs to cooling towers and or chillers, a lot of times adding VFDs to cooling towers can allow you to save, you increase fan energy, but reduce energy required by the chiller to actually provide chilled water. A lot of times upgrading pneumatic actuators to electronic DDC controls. This isn't necessarily more inherent, just upgrading technology, but with a lot more electronic controls, we can be a lot more precise and have precise measurements that are fed back into a BMS system, and a lot more data available to review and control logic and make adjustments relatively smoothly, which is the unlikely scenario with pneumatic actuators. In commercial buildings, this is actually becoming a really common recommendation for us, especially in schools that don't have showers and office spaces. A lot of times, just a big 200-gallon or 130-gallon hot water tank is installed. Most people wash their hands really quick in under 5 seconds or under 30 seconds. And don't even give a chance for hot water to be used, but you're constantly heating 120 or 200 gallons of hot water. So we recommend in these cases where you're just using a sink to install electric point of use instantaneous heater. Soft start equipment, just schedule equipment on and off to maximize demand reduction. Starting everything at once can ratchet your demand charge and cost more for the facility. Sequencing of boilers, chillers, and compressors. This has a lot to do with we see a lot of buildings that have the sequencing of boilers, chillers, and compressors. They have the capability to do it, but the control logic prevents it from doing it effectively. A lot of times spaces are constantly overheated and overcooled in succession because the control isn't allowing them to have a kind of a reset or a time delay between the sequencing. And the sequencing is based mostly off of time and not space conditions. The countermeasure controls for air handling units based on enthalpy. Essentially looking at what the enthalpy is, so the temperature and humidity of outside air, and when it's cost effective and advisable for the building, bringing in that outside air as opposed to heating or cooling outside air. Operating garage supply and exhaust fans, these are almost always left on 24/7, but installing CO level monitors allow us to turn those supply and exhaust fans on and off based on CO concentrations or carbon monoxide concentrations built up in the parking garage. We have air-to-air heat recovery. So this is really installing energy recovery ventilators in a lot of climates, especially when it's very cold outside. But you have a lot of waste heat, such as from science classrooms or science labs that may have fume hoods and other kind of high heat content exhaust fans. Is allowing that energy to transfer to the supply side and kind of preheat air before it's mechanically heated. CO2 demand controlled ventilation. Many times this allows us to kind of accurately bring in more fresh air for a building, and necessarily doesn't necessarily have an impact on energy efficiency, but in areas like conference rooms, auditoriums, gymnasiums, where energy occupancy is sporadic, it can allow us to kind of drop down ventilation level to a minimum and have energy saving. Then controls optimization. Again, just optimizing controls, looking at the logic, seeing if it makes sense, and making sure that controls are actually based on operating conditions. And lastly, trend data. Knowledge is power, using things like data loggers in a BMS system to look at data over time. It gives us really insight into how a building performs under different conditions and allows us to optimize the building and really trim the fat with that building based on historical data. So real quick, I don't need to go through all the financial calculations, but just to make you guys familiar. So didn't go slow. So the first one we have, pardon me if I'm going fast here, we've installed net cost. It's always important to include things like material costs, labor costs, and subtract any applicable incentives. So you're actually dealing with the true cost of the ECM. Cost savings, we look at the average utility rate and account for any demand charges. Operation and maintenance charges actually become an important factor. If you're installing new technology that may require more maintenance or less maintenance, that should play into your total savings package. And these are just kind of the most common terms that we use. We look at annual cost savings as well as lifetime cost savings. It's important, especially with equipment such as LED lighting, to look at kind of a lifetime cost, how many hours or how many years that equipment's supposed to last. So not only looking at the kind of the annual payback, but the lifetime payback, simple payback period, looking at return on investment, internal rate of return and net present value, accounting for the time value of money, inflation rates, and looking at kind of a total incentive package and financial package and how it pays back both annually and over time with inflation rate. I think I'm going to end the presentation there. The last few slides are just going through some of these calculations. We will send out this presentation to each of you in the recorded format. A lot of these things I had already discussed. These last slides just show you kind of how these calculations are conducted through Excel or by hand. And that concludes my presentation. So I think just to mention commissioning one last time, this is really, there's an operational drift that occurs and making sure that equipment is installed to design conditions, and also after it's been installed to make sure it's kind of consistently over the years trued up to the design conditions and to current conditions. There's a couple of resources on here. There's Portland Energy Conservation Institute. There's some great information there to kind of explore the world of commissioning and the sample forms for commissioning. There's an advanced design guide, the whole building design guide that I mentioned before, and just the IPMVP, which I had mentioned, the measurement verification protocol, as a free resource that you can get online. The HIA, I'll open it up for any questions if anyone has any questions, and if I haven't answered any of your questions, then I can reply to you directly via email or via writing. I'm going to go through the questions right now. So I had a question: how to benchmark for a multi-use facilities such as a house of worship which has a school attached. Essentially what you're going to do here is that you have to assign space types. So with the total floor area of the building, you're going to break it down. So however much area is house of worship versus how much is school. You're going to assign the different floor areas. So if you have a 100,000 square foot building and 40,000 of it's school, 60,000 is a house of worship, you're going to put that in the portfolio manager. Kind of a dominating factor of how the building gets rated is whichever space type has more than 51% is what category that building's going to fall into. If you have a case where you have a multi-use building where there's no dominant space type, which means that there's no space type that's over 51%, then the building's going to be considered kind of a mixed-use building that cannot be benchmarked, meaning that there's no certification available for that building. All right, I'm looking through the questions here. Is there a website available that shows the expected hours per year that ambient air is expected to be within various 5-degree Fahrenheit bins? Not that I know of. There's a lot of website out there. Actually, the eQuest software, looking at a typical meteorological year, you can actually output hourly ambient temperature and relative humidity, wet bulb, dry bulb temperature. We typically put it into 5-degree bins ourselves. So looking at it and then limiting based on outside temperature, we can put it into 5-degree bins. And then we know by percentage how many hours that building's within each 5-degree bin. There is a lot of the data loggers actually have an open connection to them. So if there isn't hobo data loggers available that measure things like gas flow, I'm not sure exactly what equipment specifically would measure gas flow, but it does take signals from a lot of other equipment. So if there isn't a data center available and you have that information, it can be plugged in. Okay, when a site survey is planned, are there many steps you take to ensure you're getting access to all pertinent systems? Yeah, we usually request full access to all spaces within a building. As a best practice, we always access and record 100% lighting inventory. There's a lighting fixture in every single space in the building. We have run into issues where maybe we go into a prison, we may go into a government building that doesn't have access to specific areas. The best we can do in those situations is assume that based on square footage, that area is like the rest of them. And looking more at the power density of typical what the building watts per square footage is used, and assuming it's the same for that space that we weren't able to access. Do you have any experience on energy audit, tropical weather conditions, not space heating? We do. We have worked on a couple energy audits. Like I mentioned, Bermuda. We've done work down in Florida and down in South America, where we were kind of blind, where there wasn't a relevant rating system or benchmarking tool. What we had to do in this case is look at weather data and make assumptions and break everything on a per square foot and a per temperature basis. Look at things like humidity and temperature, and do our best with how we evaluated that building. A copy of the presentation is going to be sent for those who have paid and have been on this call. For your reference, especially if you guys had audio problems, you can feel free to contact us and we can answer any questions. Do we submit verification reports to your clients after installation? What parameters do you measure on verification reports? We do. Our company is an energy consulting company. We don't do performance contracting. So we submit verification reports showing that a system's been commissioned, that it operated either as it was planned or that it wasn't operating as planned. We usually take the role of a third-party verification when we get involved with verification, meaning that there's no financial advantage to us, that we're simply just stating whether equipment or building responded or performed as expected. So we do include that in a report format to the client. And then I think that's all the questions that I see right now. What are our power plants doing about the 70% losses? That's a good question. Actually starting kind of down south in the southwest, you'll see a lot of implementation of kind of the smart grid you'll hear. They're finding ways to kind of minimize their distribution losses, minimize their generation losses. They're using cleaner sources of energy. Specifically in New Jersey is very progressive, where they're starting to supplement a certain percentage of their total energy generation is from renewable sources. Electricity is unique in the sense that there is a renewable option. There's solar photovoltaic cells that can be used to either offset electricity usage or supplement kind of the generation for the power plant. Okay, I have one question. How do we determine the investment a client must pay to do an energy audit? The energy audit is really market rate. So looking at a building, looking at kind of what equipment's installed and how big the building is. We have a competitive price that we'll go out and just like any other contract, we can send you a proposal and bid on a project. A big factor that plays into this is incentive programs and regulation. If there's regulation in a certain area that's driving a lot of business our way, we kind of meet minimum regulation and take on a lot of audits, and maybe our prices might be lower in those cases. If it's a market rate building and we're kind of have an ultimate goal in mind that we have to reduce energy by a certain percentage, we'll price it based on how aggressive we have to be to work with the client to reduce that energy. Also incentive programs, depending on how much they're kicking in, we can lower and adjust their price just accordingly for the client. Are there any equipment combinations that you found that have skewed your numbers expectedly? The short answer is yes, all the time. It comes with experience. The more data we trend, the more recommendations that we make. There's always going to be factors that affect different equipment. One common one is just doing lighting. A lot of people do lighting because it's cheap and it's a cheaper measure. It has a good payback, and don't pay any attention to their heating or cooling system. Lighting actually does have a significant impact on the heating and cooling system. Lighting gives off a lot of waste heat. This can actually increase the heating usage of your boiler a lot, and also conversely reduce cooling consumption a lot. So we have had that where we've been involved and weren't involved with the lighting, and the lighting was reduced. And we needed to go back and account for it in our calculation. How do I make sure that the indoor air quality is maintained after you do changes in the existing system? For example, implementing demand control ventilation may result in high CO2 concentration. Usually with demand control ventilation, the demand control ventilation is going to be based on CO2 concentration. Specifically speaking, when we say demand control ventilation, a supply fan is going to provide outside air based on two things, outside air damper position and the speed of the fan that's serving an area. What we do is we install multiple CO2 concentration. It's best to install it at the zone level, not at the system level. So if we have an office area that has conference rooms and has different VFB boxes, we want CO2 sensors at each of those locations. So we know that we're not depriving one area of oxygen and supplying or letting CO2 build up in another area. I think that's it. I can answer, if I didn't answer anything, I can send out emails later. My contact information is on that last slide. Feel free to contact me. That's my office phone number. I can also give my cell phone number. Well, it's kind of daring to do that. It's 646-484-1629. But we really are a company pride ourselves on really trying to help people. There's not a big financial gain for helping people for us, so I'd welcome any questions. You can also email me. If it's data logging specific, I can work with OnSet, or you guys can work with OnSet directly. Their contact information is on there to help you answer a lot of your questions. I'm sorry for the technical difficulties today. We kind of condensed this presentation and try to get in a lot in 2 hours. If there's any topics you'd like explored further, I'd highly recommend really writing what you think of the presentation on an evaluation form that I'm going to email out to you tomorrow. We can always put on more presentations and redo this one, or send you guys any information that you may need. And I think that's it. So thank you guys for your time. And please contact us if you have any questions, and hopefully you learned something today. All right, thank you.